Welcome everyone, and thank you for joining us for the second to last stream of Live in Space Days 2025. My name is Szymon Grodzki, and I'm here on behalf of the Polish Astrobiological Society. It's a pleasure to introduce our guest, Przemysław Jarosiński from AstroBio and AstroLife. Today's session takes us into the rapidly evolving field of exoplanet science, how the major detection methods developed, what we've learned from more than 6,000 confirmed worlds, and what are some of the more unusual planets that can tell us more about possibilities of life beyond Earth. The floor is yours.
Thank you, Szymon. Hello, everyone. It's an honor to be here and to talk to you about my favorite subject. I'm a chemical engineer working at Warsaw University of Technology, branch in Płock. In my PhD studies, I studied crude oils, but all of this is my job, whereas space, exoplanets, astrobiology are my passion. That's why for almost 5 years I've been working for Mateusz Kalisz, contributing to AstroLife YouTube channel and Facebook page. And since last summer, I'm proud to be a member of Polish Astrobiological Society. Compared to others, my talk will be probably more entertaining than scientific, but I hope you'll still enjoy it. This is my plan. Items 2 and 3, the discovery methods and planet examples may be mixed sometimes. After the scientific part, we'll close on a more speculative note. First things first, Star Trek inspired both the title and the talk, as you could suspect. If you're new to Star Trek, Strange New Worlds is a great place to start. It captures the best of the franchise in a modern, beautifully realized visual style. You'll also spot a few Star Wars references in my presentation. If those are not your thing, blame the exoplanet science community, not me. So let's begin. And let's begin with planets around the dead star, or maybe undead star. Not Death Star, no Star Wars here. Until 1999, 91, exoplanets were only a speculation. These two guys changed that. Using the famous legendary Arecibo radio telescope, they received unusual signal from the pulsar PSR B1257 plus 12. The pulsar is a highly magnetized rotating neutron star that emits beams of electromagnetic radiation out of its magnetic poles. Neutron stars are the leftovers after a supernova explosion. In Leach case, as it was called later, the rotation period is just above 6 milliseconds, which means that it rotates 160 times per second. It's 40% more massive than Sun, while its radius is only 10 kilometers. And it's also quite hot, as you can see on slide. In 1992, Alexander Wolszczan and Dale Frail noticed that the motion of Leach was undergoing strange disturbances. To explain these irregularities in the cosmic lighthouse motion, they hypothesized that the star's motion was influenced by the planets orbiting it. Further research confirmed their claims. There are 3 planets orbiting Leach. And what we know about them? First of all, their names match the star. Leech is a fictional undead creature, and the planets' names are also related to the world of undead. The closest planet is the smallest and much lighter than the other two. Orbital periods are rather short compared to Earth, but not so short among other exoplanets. Unfortunately, we don't know the radii. And what about life in such places? A pulsar's magnetic field is a source of microwave radiation accelerating elementary particles. A continuous rain of ions accelerated to high speeds falls on the planets. Ionizing radiation on the surface is deadly to known life forms. However, on Earth, the bacteria Deinococcus radiodurans can survive unarmed a dose of ionizing radiation hundreds times greater than lethal to humans. Such great resilience of known life forms raises hopes that evolution on other planets may have created organisms capable of surviving even in the race of a pulsar. Okay, but let's move to another method, a very important one. The radial velocity technique was used to detect the first planet orbiting a sun-like star, and it ultimately earned a Nobel Prize. Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b in 1995 and received the 2019 Nobel Prize in Physics for their work. I'll tell you more about the planet later. First, let me explain how the method works. And of course, I'm disappointed the prize didn't also recognize Wolsztyn and Frail. In the animation, you can see how a smaller object, an extrasolar planet, orbits a larger object, a star, and produces changes in position and velocity of the latter as they orbit their common center of mass. Doppler spectroscopy allows us to detect periodic shifts in radial velocity by recording variations in the color of light from the star. When a star moves towards the Earth, its spectrum is blue shifted, while it is red shifted when it moves away from us. By analyzing these spectral shifts, astronomers can deduce the gravitational influence of extrasolar planets and assess their mass. Why did I say assess? Because the mass obtained by this method is the minimal mass of planet, and the actual mass depends on the inclination. Radial velocity method doesn't give the mass. Instead, we have m sin I. The argument of sine is inclination to the plane of the sky. So if we look at a planetary system face on, like on the left, the inclination is 0, and in the spectroscopy data, we can't see any shifts corresponding to the movement of a star. And if the planet and star are in our line of sight, like you see on the right, the inclination is 90 degrees, the sine equals 1, and in that ideal case, our m sin I is the exact mass. As you probably suspect, most of the planetary systems lie in between the two situations presented here. How the inclination can be determined? Other methods like astrometry or the transit method come to the rescue. If you're interested in how radial velocity data looks, I have an example here. Radial velocity measurements of planet 18 Delphini b. From the observed amplitude, you can calculate the mass. Of course, m sin I. What about 51 Pegasi b? It's a hot Jupiter. Hot Jupiter is a gas giant orbiting its star in very close proximity. These are the best planets to be detected by radial velocity method because they are massive and orbit close to their stars, which means they can wobble their stars pretty strongly. 51 Peg b is the first known hot Jupiter and a good example of this class of exoplanets. It's located 50 light years away in the constellation Pegasus. Its mass is about half the mass of Jupiter, but the radius is probably larger because its superheated atmosphere must be puffed up into a thick but tenuous layer surrounding it. The orbital period is only 4.2 days. Of course, we cannot imagine life developing in such harsh conditions. Dimidium, which is the official name of the planet, was discovered 30 years ago. Now we have over 1100 exoplanets discovered by radial velocity. Let's talk about another method. In the 1980s, Polish astronomer Bogdan Paczyński proposed a gravitational microlensing method for searching for faint or non-luminous objects. In a 1986 paper, he argued that even if gravitational microlensing were not detected, the data collected would be used to discover many variable stars. This pioneered modern CCD sky service. Professor Paczyński was the initiator of the optical gravitational lensing experiment, OGL, which is a Polish astronomical project based at the University of Warsaw that runs a long-term variability sky service since 1992. The main goals are the detection and classification of variable stars, discovery of microlensing events, dwarf novae, and studies of the structure of the galaxy and Magellanic clouds. Since the project began in 1992, it has discovered a multitude of extrasolar planets. The project has been led by Professor Andrzej Udalski since its inception. And how does gravitational microlensing work? A light from the distant star is bent due to the gravitational field of an intervening foreground star and its orbiting planet, resulting in at least 3 unresolved distorted images. The change of their solid angles obtained on the sky corresponds to an observable brightening of the observed source star. Here you can see some real data for a microlensing star. And in this ESO animation, an influence of the planet is very well presented. The wide and high peak corresponds to the star passing in front of another background star. And when the planet orbiting the star, orbiting the foreground star becomes the micro lens in front of the background star, we can see an additional tiny peak. Like this, and let's move on. As an example of planet discovered by microlensing, I chose OGLE 2005 BLG 390LB, nicknamed HOT because which is a reference to famous ice planet in Star Wars. A super Earth is a type of exoplanet with a mass higher than Earth's, but substantially below those of the solar system's ice giants Uranus and Neptune, which are 14 and 17 times the Earth's mass respectively. The term super Earth refers only to the mass of the planets and so does not imply anything about the surface condition or habitability. Hoth is quite the opposite to 51 PEG-B because it's very far from its star and from us as well. This is the advantage of microlensing, unlike most other methods which have detection bias towards planets with small or for the direct imaging large orbits. The microlensing method is most sensitive to detecting planets around 1 to 10 astronomical units away from Sun-like stars. An astronomical unit is distance from Sun to the Earth, of course. The distance means that this kind of distance means that Hoth is very cold. If it is a rocky world, the temperature that low would make it likely that the surface would be made of frozen volatiles, substances which would be liquids or gases on Earth, like water, ammonia, methane, and nitrogen. They would all be frozen solid, but maybe there's some internal heat left and life flourished beneath the ice. We shall go back to this idea. First microlensing planet was discovered 22 years ago. Now we have 262 of them. The most important method of exoplanet discoveries is the transit method. The most prominent space observatories that gave us hundreds or even thousands of candidates and confirmed planets were Kepler's Space Telescope and a transiting exoplanet survey satellite. While Kepler looked at quite a small patch of the sky for a long time, TESS observed all the sky but in shorter periods. Both telescopes gave us plenty of exoplanets, but what the transit actually is, when a planet passes directly between a star and its observer. I thought it froze. Okay, it's working. It dims the star's light, but by a measurable amount. Larger planets block more light. This animation compares two planets of different sizes and shows the changes in the light curves. But these curves are almost never so clear and unambiguous. More often they look like this. I encountered this light curve in citizen science project Planet Hunter's TESS on Zooniverse. Unfortunately, I wasn't one of the people who spotted it first time. It was already a candidate. Its confirmation as a planet came in 2023. Can you see the transits? There are 3 of them. First one is here. Another is here. And the last one seen is here. The first known planet to be discovered with the transit method was OGLE TR56b. The first planetary transit observed by already known exoplanet was caused by HD 209458b, but instead of them, I'd like to tell you about a famous example, Kepler 16b. Kepler 16b, sometimes called Tatooine in reference to Star Wars planet, is a circumbinary planet, just like the mentioned Tatooine. We all remember, all who watch Star Wars remember Luke Skywalker looking at two suns setting. So that's the reference. Circumbinary means that it circles around two stars. The stars orbit each other, or shall I say the common mass center, and the planet is orbiting them. As you can see on the slide, is a gas giant, but much smaller than Jupiter, and it's very cold. We have density here because when you combine the radius derived from transit with mass got from radial velocity method, we can calculate the density and conclude something about the composition of the planet. So it's very important to have both these parameters from these two methods. I decided to mention Kepler 16b because it's a brilliant example of a phenomenon called transit timing variations. The gravitation forces in the system impact the movement of planets, so the transit period, in other words, the time between the transits, may vary. In the picture, you can see that 230 days passed between the planets to transit in front of the larger star, and 221 days between the next two. So the difference is almost 9 days, and even 24 days in case of transits in front of smaller star. And this phenomenon can be caused not only by stars, but also other planets. So transit timing variations is helping to discover next planets in known systems. The variations are smaller than here, but still useful. Okay, I talked about one planet orbiting two stars. So let's try something else. Here you can see how the transit look when there are multiple planets in the system. The first one and the other two will come together, almost together. So the light curve is a bit more complicated. And the famous multi-planet system is TRAPPIST-1. There's no point to talk about each planet alone. Here we can see they are all rocky planets similar to Earth, Venus, maybe Mars. What's amazing about these planets is that because they formed around a very small and cold star, they are all very close to the star and to each other. If you take a look at the orbital period column, you see that the farthest planet orbits the star in less than a month, and half of them does it in less than a week. And this is my favorite picture regarding TRAPPIST-1. TRAPPIST-1 system would fit inside Mercury's orbit. The closest planet, TRAPPIST-1b, is as close to its star as Callisto, one of the Galilean moons, to Jupiter. By the way, the TRAPPIST-1 star is only slightly bigger than Jupiter itself, as you can see on the left. How about the light curves in such extraordinary system? Well, if you separate the data, they look very nice and clean. But if you don't, the light curve goes wild and chaotic, but in my opinion, it's beautiful chaos. First planet discovery by transit method happened 22 years ago. Now we have 4,466 of them. So nice progress. And the last method I'd like to tell you about is direct imaging. This technique contribution to exoplanet science is not as significant as others, but its discoveries appeal to the imagination. Direct imaging is, as its name states, the only direct observation technique There aren't many planets possible to detect this way. They have to be bright, which means quite big and hot, and on distant orbits. But if astronomers directly image planets, the images as well as created animations are spectacular, and I will show you some of them. Beta Pictoris b is quite a big planet. It's 8 times more massive than Jupiter, very hot and on rather distant orbit. In 2014, the rotation period of Beta Pictoris b was calculated from the broadening of its carbon monoxide infrared absorption line. This makes it the first extrasolar planet to have its rotation rate measured, and the rotation period was later refined to 8.7 plus minus 0.8. It's slightly faster than Jupiter then, which rotates in 10 hours. But my favorite example of directly imaged planet, or shall I say planets, because there are 4 of them, is HR 8799 planetary system. Here you can see some data. They are all much more massive than Jupiter and in distant orbits. Here we have the comparison of this system to our system, or to be precise, to Neptune's orbit. And here on the left is the image from James Webb Space Telescope, and on the right an animation of created based on pictures taken by Keck telescope over the years. I'll give you a second to admire. First directly imaged exoplanet was 2M1207b. It was observed 20 years ago. HR877 system was discovered in 2008. Now we have 88 exoplanets directly imaged. To sum up this part, I'd like to show you some stats directly from NASA Exoplanet Archive. The numbers you've seen earlier in the presentation come from this website. As you can see, during 33 years since the birth of this branch of astronomy, the scientists discovered over 6,000 of them. I find it quite an accomplishment. So now we reach to more entertaining part of my presentation. If some of you got bored or sleepy, I hope that I'll get you a bit excited in the end. I'm going to read some dialogues between hypothetical scientists from other worlds. These dialogues come from the book written by Trefil and Summers, professional scientists, but also enthusiasts of searching alien life. Mike Summers was involved in New Horizons mission to Pluto. The dialogues come from Polish edition and were translated by me, but among these stories is one imposter. One story is written by ChatGPT, instructed by me. I wonder if you are good AI detectors and if you would guess which one. After the dialogues, I'll invite you to a quick thought experiment using the Drake equation. Because of every exoplanet or astrobiology course, lecture, or talk seems to include it, so mine can be the odd one out. Let's travel to ice planet Hoth, discovered by Ogle project. Assume it's a rocky core planet covered with ice, but still has some geothermal heat. Life emerged, evolved, and even produced some scientists. Here goes the dialogue. Have you heard that scientists at the University of the Seventh hydrothermal vent proposed tunneling upward? They want to break the ice? What for? They say the recently discovered variations in heat signals come from the region beyond the ice. You mean the ice actually ends? That's what they believe. It makes no sense. There can't be water above the ice. Any surface on the other side would be too far away from the hydrothermal vents to melt it. How could there be water without hydrothermal vents? What's more, it's known that life is impossible without a hydrothermal vent, and such a vent cannot exist without a rocky surface. Yeah, a ridiculous idea. Okay, now let's use warp factor 9 and jump to Kepler 16b. Assume there are some tidally heated moons around it and listen what their scientists talk about. Scheduling next month's survey? Make sure the warm, cool beat aligns. Double sunsets push the jet streams north that week. Already checked the twin day tables. With the cooler star flaring mid-cycle, we'll get extra ionization. Good for comms, bad for high altitudes. Perfect. By the way, did you read about the single sun system? One light source, no redundancy. How do they keep their current calendar stable? With only one diurnal driver, weather must be monotone, then snap chaotic when it shifts. And tides. Two gravities give us proper mixing. With just one, nutrient loops must crawl. Energy planning there must be brittle. One star sets the rhythm, one night, one day. If it hiccups, the grid has no second light to smooth the load. And imagine navigation. No second shadow to fix bearings and festivals with only one sunset? Half the poetry is missing. Take our normal. Two irradiant cycles, a sky that breathes into tempos, and logistics tuned to the barycenter, not that stark single stars minimalism. And the last dialogue comes from Trappist 1. Have you heard a planet about the size of ours has been discovered in the habitable zone around the star Sol? You mean the star 40 light years away from us? Cool. Sure, but it's a strange system anyway. All the planets are farther from their star than we are from ours. What's more, Calto 47 says that from the surface of each planet, the others look like points of light, basically like stars. And if you can't even see neighboring planets, who would think about space travel? What for? There's speculation that this newly discovered planet might have a moon, but it would be too small to hold an atmosphere. Who'd want to colonize a place like that? Well, if life forms developed in the oceans of this world and went on to create technology, they wouldn't have anywhere to migrate. They'd be stuck on that one planet. Sad. So here goes the question to the audience. You can write your answer on the chat if you want. I'll give you a moment to think. Which story was written by ChatGPT? And this is the answer. The story from Kepler 16b or its moons. Congratulations to everyone who guessed correctly. I included these stories, these dialogues, for two reasons. First, to show that what feels ordinary on Earth can be extraordinary or downright crazy elsewhere, and vice versa. So we should keep our minds open when we consider life in the universe. And second, I wanted to remind how lucky we are to have avoided these hazards, these dialogues mentioned, and how lucky we are to live on our beautiful, hospitable, warm, pale blue dot, like Sagan put it. And finally, I promised a quick thought experiment, so let's begin. The Drake equation is a probabilistic argument used to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. Probably most of you have heard about, maybe everyone, but I don't think many of you remember what the particular symbols in the equation mean. So let's go through them. R star is the average rate of star formation in our galaxy. FP informs about the fraction of those stars that have planets. NE is the average number of planets that can potentially support life per star that has planets. FL is the fraction of planets that could support life that actually develop life at some point. While the Fi is the fraction of planets with life that go on to develop intelligent life, the civilizations. And FC is the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. While finally the L is the length of time for which such civilizations release detectable signals into space. And we can divide the factors into two groups. First three can be estimated using actual scientific knowledge, whereas the next four are definitely more speculative. Current data says that Milky Way is now forming one star per year. To be precise, the overall number is higher, but we're talking about dwarf stars like Sun or smaller, not big blue, shortly living giants. It's reasonable to assume that every star of this kind has at least one planet, so 100%, so the fraction is 1. Based on our solar system and observations of other ones, we can assume, maybe kind of optimistic, but still sensible, that there are 4 planets in habitable zone per star. As for the fraction of planets actually developing and supporting life, 0.8.2 seems fair to me. Among these planets with life, I think 10% won't have intelligent life. And among this intelligent life, 10% would be able to send signals through space. I estimate the time they could continue to do it as 250 years. All in all, these numbers give us 2 civilizations in Milky Way. If you think I was too optimistic, let's try to be skeptical. I will leave the star formation rate as 1 per year, but decrease all the other factors. Let's say that 20% of our dwarf stars don't have planets, so the FP would be 0.8, and only 2 instead of 4 planets per star can support life. And let's decrease each of the speculative factors by dividing them by 10. We get 0.00008 civilizations per galaxy. Okay, we got 2 civilizations per galaxy in the optimistic approach and many less while being skeptical. What does it mean? Please take a look at the Hubble Ultra Deep Field published in 2006. How many galaxies are in the picture? I'll give you a few seconds to take a guess. If you wish, you can write it on chat. People who know cannot answer. Don't spoil. And the official answer is about 10,000 galaxies in this image. So optimistically, we're looking at 20,000 civilizations, while skeptically at almost 1. But we have to consider one more thing. How large piece of the sky did Hubble cover while taking this picture? And I can tell you that this is a square 3.4 arc minutes by 3.4 arc minutes. While, for example, diameter of the moon is about 30 arc minutes. So the full moon on our sky is about 63 times larger than Hubble Ultra Deep Field. I put 9 ultra deep fields on the diameter of the moon to visualize. And our final conclusion here is there are about 50 civilizations somewhere behind the moon, wherever the moon is. Of course, very far away, millions or billions light years away. And if you agreed with my optimistic approach, then by looking at the sky on the area of full moon, you're looking at well over 1 million of civilizations. I know there are many ifs, many simplifications, many speculations, but I think it's mind-blowing. And with this hypothetical but still mind-blowing thought, I would like to leave you for now. These are my sources of information and inspiration. And that would be all from me about exoplanets, life, and space. Thank you for listening. I'm ready for some questions. I hope not difficult ones.
Hi, so thank you very much for your lecture. It was very interesting. I would like to remember that we have next lecture at 8 p.m. And now we are ready to take some questions from the audience. The first one will be from Arsenic Ginger. What about exomoons? And are there any progress on that topic and or any research focusing on discovery of these?
I heard about some supposed exomoons, but we do not have any confirmed until now. But it's progressing. It's progressing. I can't say any details, but I'm optimistic with new telescopes, new possibilities. I think we will finally discover some exomoons. People work on it.
All right, thank you for that answer. And actually, that's a great segue to my next question. So, with limited time of telescopes and new instruments coming online, what observing strategies and target choices should the community focus on to give us the best chance of identifying reliable biosignatures in the coming years?
Well, difficult question.
Well, as in, what systems do we, most prioritize? Is there any process of selection when we decide what we want to study?
Well, the problem is we are a bit biased by the methods we are using. The transit method or the radial velocity method are designed to discover planets very close to their stars, and there are there's no life there as we know it. So based on similarity to our system, we should look for these signatures in similar systems. But this is the problem that it's hard to align with the short time when the transit of planet similar to Earth on the orbit similar to the Earth's orbit, because the transit would be very short. It can be hidden in the data, and it's very rare, once a year, so it's hard to align with the time.
Sure thing. Thank you for that. And last question for today. Are there many false positives? Do we actually actually which detection method is the best when it comes to least false positives if we have any?
Well, I won't tell you about which the method is the best, but I think there are many false positives. I met very much of them while trying to work on Planet Hunter's test. It's in case of transit method that Planet Hunters worked on, because it worked on test data. The most common false positive was eclipsing binary, the other star eclipsing the bigger star. Sometimes such an event from behind the star of interest, but there were a lot of them, eclipsing binaries.
All right, thank you. And actually, how long do we have to study such a solar system so that we can actually be sure that there were no false positives? It's just like 5 years, 10 years? How long does it take?
It depends on the period of the planet, because if the planet has very short period, and we have one observatory to find it, and a month later another observatory will find it in a month, then we have the confirmation. But if the period is 3 or 6 months or more, then it can be, like you said, few years.
All right. Thank you for this section, and thank you for your great lecture. And thank you everyone for coming. And I also recommend checking out our next session at 8 p.m. today. Thank you once again, Przemysław, and I'll see you soon.
Thank you very much.
Bye.